Good afternoon, everybody. So I have a question for the audience, which is, suppose that you could miniaturize electrical systems, optical systems, whatever. You could miniaturize a physical thing. Would it be possible to have a conversation, an intelligent, semi-intelligent conversation, like the type that you have with ChatGPT every day, I'm sure, right? I do. It's pretty good, but with something the size of an ant. Can I, actually I'm curious, my electrical engineering students tend to say no, but I want to see if anybody says, yes, this is possible. Can I see anybody think this is possible? Can I have a conversation with something the scale of GPT-4 that fits on the size of an ant? So the power here has to be like microwatts. Anybody? Okay, there's one. Okay, that's possible. There's no physics that says no, right?
If you work on it, it's possible.
Oh, no, that's then no. But so that's sort of like the thing I want to get into here, and I know this is a display workshop, and I'll touch briefly on displays, but luckily I'm represented by some amazing people that I'm working with, so I'll focus here instead on more the perception, and so in particular the problem is one of computing, and so if I have that conversation with the ant, I give it some input, x, and I would like it to return some output, f of x. If this is a function that performs that map that is learned, we call this machine learning, or perhaps artificial intelligence. And here we have trained the model parameters of this function by one of the various methods that are used in machine learning. So the inference then here is this mapping from my question to its output. In the case of the ant, like there's a bunch of stuff involved, like large language models, of course, next token prediction, transformers. But typically, I would like my ant to also have a world model. I don't want it to just do next token prediction. I want it to be, pretty smart. And so in the end, though, it's a mathematical task, and we have no physics that says that you can't do this on a many orders of magnitude lower power consumption and swap altogether. So this is what I want to talk about here. Having a conversation is one of the inference problems. What am I talking about? But there's also vision. What if I want this to be multimodal, like I wanted to show an image and so on, and maybe this connects to the displays in the sense that the Laya display, maybe it would be better if it could see who's looking at it, and it can then in real time compute the image to project back to the viewer, etc. And so this touches in the hardware side on work that I do with my team at MIT and with collaborators at MITRE Corporation. We'll hear later from Henry Wen, who is a scientist with MITRE Corporation, on quantum control. And in the case of quantum control, you have this a problem that matches closely with the approach we take to the machine learning kind of inference engine, and the problem is one that I illustrate here. I give you an example. So the kind of physical hardware control systems you need are little inference machines. So like imagine that you make a quantum computer based on an array of atoms, cooled in this case by laser cooling techniques to microkelvin temperatures. They're trapped in space, and you ask them a question. So it's you ask, what is your state? What is your state collectively? And this is the first step of quantum error correction. Then I take the output and I decode it, and then I act back on that. That's feed forward in quantum error correction. So in the end, it's an inference problem, and then a matter of optimizing a policy. So I take an input in, as is in the physical domain. I transform it into a good set of measurements. I perform measurements, projecting the input states to some measurement outcomes. Then I have to compute on these outcomes, and then I feed forward. Okay, so these things for us increasingly in quantum control are things that are learned and not idealized algorithmically. And a similar approach happens in machine learning signal processing. Like in this case, the input doesn't come from a set of atoms that you're trying to use for your quantum computer, but perhaps from a video stream from for a driving car or something like this. So really, this is in the context of the, well, I think we're currently in a sort of a renaissance in computing. This touches on quantum computing, and actually the type of machine I showed you in the previous slide with these ultra-cold atoms is actually at the basis of a company I co-founded with colleagues at MIT and Harvard. And here's one of these. This is Professor Mikhail Lukin, who is with Quera Computing at GTC 25 at NVIDIA's annual developer conference. And there's a close connection between machine learning, the compute that needs to happen for perception, and quantum control, and by extension, quantum computing. So this is also an example of a specialty processor, just like machine learning inference machines are specialty processors. And we know that it costs a lot of energy to train these specialty processors, especially in machine learning. And the types of machines that are used to train these deep neural networks are massive. And here's an example of such a data center. This is a Google data center. And a lot of the data, when you look at the data streams inside these machines, are redundant. For instance, just one way this is true in training, but especially true in inference. If you think about an image on which you wish to perform image recognition that I take with my phone, I send it to the cloud. It goes to a data center like this, and then some image inference, some vision model performs inference for me and sends it back to me. And this happens not just for my channel, but for thousands or millions of channels in a city per day, right? So this kind of a machine, this data center, runs the same neural net over and over again. So if you want to get to something that makes this end possible, one possible way to do that is to reduce the energy cost of running inference in these kinds of parallelizable problems by data fan-out. So in particular, suppose that you had disaggregated memory access in a data center like this, where a server sends to these millions of machines the same models, which they can then use in real time to process a task. Then they no longer have to retrieve the model from memory locally, which is actually the main bottleneck, but can run in real time and it turns out, low energy consumption. So this is possible use of physics number one to make this dream of this tiny ant conversation possible. And so here, in the remainder here, I'll tell you about the lessons we've learned and how far we've come to be able to do inference with far lower energy consumption, order of magnitude lower energy consumption, and the key algorithmic lessons we've learned and hardware we've developed along the way. So here's one way to, so suppose that you have an input which this could be a vision task. Suppose that you have an input here of some number of optical fields that are an optical field that's sampled in this case by 6 channels. Obviously, it's super resolution, low resolution in this example, but in the vision neural net, early on in the early layers are convolutional layers. So you could sample the optical field of an input and send it through what is implemented here, matrix that performs this kernel of the input convolutional layers. And you can encode that kernel into hardware. So this is sort of an in-memory computing architecture in this case, where in this device here, you encode it into phase shifters. As light propagates through, this optical field transforms to an output, and then output realizes a matrix vector multiplication. This is one step of the deep neural inference. The important thing about this, although this is not like a scalable architecture, or not one that we pursue nowadays as a scalable architecture, there's an important lesson here, which is that on this kind of an optical processing machine, the amount of effort needed to perform matrix vector multiplication scales as order n, where n is the number of samples that you have on the input and perhaps on the output. Chiefly on the input is the important thing. Whereas in a binary computer, performing a matrix vector multiplication of a 1 by n vector multiplied by an n by n matrix requires of order n squared operations. So the fundamental difference is that if you push some of the linear algebra into the physical layer, you can have a different scaling of the effort needed to perform a computation, n squared versus n. And this, by the way, led to 2 startup companies back in 2017 that are now really working on the big problems of hyperscale data centers in training. So I'll show you another example of performing this kind of in physics computing. Here you have an optical field, X, which is sampled at n time steps, and another field, W, which also is sampled at n time steps. You send it through an interferometer and aggregate the photocurrent produced on the differential output, and that performs a dot product. The energy consumption for this dot product, for this inner product of 2 n-element vectors, assuming that the optical fields are free in terms of their encoding. It's an optical field that comes in. And assuming that the weight is distributed and provided by a server, also for free on this inference side, that energy consumption is of order 1. You have to sample the output of this integrator 1 time for every inner product of 2 1 by n vectors. So again, a scaling advantage of order n versus order 1 in this case against a conventional Boolean-based digital computer. And so what this means in practice is that if you make computing systems that distribute computing loads into specialized hardware, and not just into specialized hardware as for example, a CPU and a GPU, but some specialized hardware like an optical processing step, then you can make machines that are fundamentally different and in some respects more powerful, at least according to the physics, than today's machines. And you can measure this here. In this paper published back already 6 years ago, we look at the energy consumption to perform multiply accumulate effective energy consumption as a function of the size of the neural net. And what you can see here is that with this kind of an approach, you can beat the Landauer bound of a Boolean-based machine. So a conventional machine is not capable by thermodynamics to keep up with a machine that distributes load across irreversible computing steps, Boolean logic, and reversible computing steps, manipulation of light before it's sampled. So that's an important lesson that we're going to use to build that ant that we want to build. Along the way, I should recognize that optical and other analog machines do have a problem with error, as do binary machines. It's just you have to be really it's a matter of doing some amount of compute in linear algebra in this analog fashion and then discretizing along the way. And that discretization step should happen before your error has accumulated beyond what you can recover. And so error correction is possible. So I'll show you now a field demonstration of this kind of an approach of disaggregated memory access. This is not imaging in this case or displays, but this is an inference problem across the network. So here you have a network of optical fiber in the Boston area. We have at MIT Lincoln Laboratory in Lexington a server. This is the machine that distributes the neural nets, the deep neural net model data to multiple clients. In this case, have to be plugged in via fiber. That's a bit inconvenient. But so these edge devices can take that model data and perform, by this kind of a physics approach that I just showed, all the linear algebra in a way that is very efficient. And in particular, here we're distributing over a 43-kilometer long fiber, to multiple clients a machine learning model, and the edge device in this case can perform inference at some at a rate of gigabit per second, with a power consumption about 3 orders of magnitude lower than a conventional GPU-based machine. And I can show you here, you can see from this that the inference accuracy is saturated at the model. So you have a machine learning model, in this case MNIST, digit recognition. It performs as well as a conventional computer does. This is limited not by the compute but by the model. So it's a model-limited inference error, but the energy consumption is 4 orders of magnitude lower. In fact, the energy consumption is so low. The energy consumption can be so low that in the optical field, looking for the moment only in the optical field, the energy needed per transmission from the model parameter is less than 1 photon's worth per model parameter that's transmitted. Which you would say, oh hell, that must be terrible signal to noise because shot noise and so forth. True. If you were trying to measure one symbol at a time, it would be bad signal to noise, but you're not. In convolutional layers or other linear algebra, you're looking at inner products. And there the signal to noise can be sufficient, and in fact much below 1 photon's worth. So, so that's data point number 3. You can be very efficient if you curate your model in a way that a linear algebra processing machine that uses physics can digest in real time. And now I'm going to get into a bit about imaging. Here's a programmable optics and machine learning perception problem. So we have an input that in this case passes through a series of spatial light modulators. In this experiment done by Leanne Bernstein, joined actually by Chris Panusky over there, we performed inference. And because there are so many modes in the optical spectrum, you can parallelize optical streams to have extremely high data rates. And because we can inference on that data rate in real time with no latency, added latency, you can in principle process at very high speed if you can process on optical fields. And again, we're close but not quite at the saturation limit of this model. The point here is that you can perform inference in principle at very high rate. So I'm going to run out of time here. So I'm going to show you some of the hardware now in the last couple of minutes. I have how many? Like 2 minutes or something? Yeah. So I'll show you some hardware examples of this proof of principle I just showed you here use spatial light modulators. So we can show that one frame at a time. We can inference super fast, great, but the frames keep on coming in an optical imaging problem, right? So can we make this fast? So here are some approaches we've taken. One is to create spatial light modulators based on liquid crystals that are infiltrated into the back end of the line interconnect layers of CMOS. This gives you a strong electric field that allows you to switch the liquid crystal molecules at high speed, and we can get to megahertz here. In another example, this also with Chris Panusky, we integrate thin film lithium niobate into a phased array, into a pixel array for high-speed phase modulation. And we did some preliminary work here integrating it with a back plane, a commercial back plane. The ant, you want to know about the ant. So let's put it together here. So the ant doesn't have a photodetector receiver, but it turns out you don't need one. As long as it can have a radio receiver, it actually works as well. In this case, we have model parameters streamed from the server. This is actually not in my laboratory, but in the lab of Tungjun Chen, who's a assistant faculty member at Duke University. And this is a long collaboration. I'll show you our paper in a moment. The model parameters are streamed by one radio into free space. There are other radios that pick that up and can perform inference by mixing with the input radio signal and its local data in real time. Okay, and we once again saturate the model performance. In this case, again, good old MNIST. It's one that really it's an easy one to use for these demos. The important point here is that you can see the energy per multiply accumulate by this in physics, in this case, making use of a radio mixer, is per multiply accumulate an equivalent of 10 to the minus 16 joules. This is about 4 orders of magnitude below conventional, the multiply accumulate energy need by conventional methods. So it's a matter of the architecture. If you can have the way to realize this, and the way we can make this kind of a thing possible is by optimizing the information flow. It doesn't have to reside on that device here. It can be maybe coming from somewhere else. Maybe it's distributed across multiple of these devices. And by this way, we think you can actually, in fact, get to if you run the numbers, you can see that you can get to the requisite energy scales. I will be happy to talk about that with folks here. So very last bit at the end here, have a look. Please stick around towards the end of this wonderful conference today, because Chris Panuski will talk about high-speed spatial light modulators produced in a foundry process, 300 millimeter wafer process here, and some really cool software that he and collaborators have been developing that will, I think, be of great interest here. The Henry Wen will talk about this thing here. This is a display, which really comes out of our quantum control efforts. But what this is a single chip light engine and scanner. This is it turns out, as I said, for quantum control and displays, the requirements for us are quite similar. So we kind of accidentally invented this new technology to integrate a laser display, to integrate the scanning mirror that is conventionally used in a laser scanner display with the modulator and light engine itself into one chip. The entire system is integrated into one chip. And so you can get high resolution, and at the same time, each beam can be modulated at above 100 megahertz rate. And it's actually an interesting side note here that this is one way, and looking forward to conversation with folks through the breaks, to realize multi-plane displays. So this thing can do high speed in one plane, but it can project multiple planes at the same time. And this is, I think with this, maybe just along the way, a bunch of companies have been founded to take on these technologies. Some from my lab, some through collaborations, and one in particular that is very dear to my heart is using generative AI to help us optimize these physical systems in the first place. And this is to use generative AI to make digital twin models. And I'm happy to talk about this after or in the break with you. So that's it. Thanks a lot.
All right, so questions? Yeah. Oh.
Given the fabrication, so what's the low-hanging application fruit for this? So what industry is begging to have something like this in the next 3 to 4 years?
I covered several things. Which one do you mean? This, like the display? The display. Yeah, so fundamentally, I think that as we now know that signal processing is inseparable from the tasks of machine learning, and conventional edge devices that conventionally sample and then signal process subsequently will be revolutionized. They will be changed because you can push a lot of the compute into the data acquisition channels themselves. So this is the programmable component of the edge device. And this is of great interest, and this allows you better performance in sensing a quantum mechanical signal, like a feedback of a quantum computer, and I think also for vision, and for other input quantities. Like we have a magnetometry example on this as well.
With the AR, you can put his ant on so that you don't have to be connected to internet. You just put it there.
Yeah.
How do you people wait?
Yeah, so so to your point here, right? Suppose that the compute also is inseparable with displays if you are taking that view. right? If you don't want to have to store playing a video game, maybe on the AR VR, so there's a compute needed, right? So how do you update the weights? So one way to update the weights is to stream them to multiple edge devices. It's just the fan out. So you have to do millions of convolutions. You can have one transmitter that transmits the kernels to the inference devices at the same time. So that fan out is useful. I think it's useful, especially in applications where you have an asymmetry in let's say the provision of the model parameters and an inference device. An inference device in this case, for example, is one that has very low power limitations, and you have somehow provide through the cloud or so you have a higher power transmitter, and that's what we saw in the. I think that there will be the end, isn't it? So you could imagine that. So we take GPS for granted. Suppose that satellites, instead of beaming time coordinates, beamed basic model parameters. Then all devices that have the ability to receive that radio wave could perform basic inference. It's on a schedule, right? But you can beam intelligence to edge devices. So yeah, it's fun.